Dear learners, I am happy to welcome you to this module. The topic for today's module is independent sets and coverings in graphs. Yes, today we are going to learn about vertex independent sets and vertex coverings. We will see definition first and later on we will learn them with an example. Vertex independent sets, vertex coverings, edge independent sets and edge coverings of graphs occur very naturally in many practical situations and hence have several potential applications. In this chapter, we will study the properties of these independent sets and coverings. We will see the definition first. A subset S of the vertex set V of a graph G is called independent set if no two vertices of S are adjacent in G. Next, let us see the definition of a maximum independent set in a graph. The definition is a vertex independent set S, that is subset of V, is called a maximum independent set of G if G has no independent set S naught with cardinality of S naught greater than cardinality of S. So, does there exist a special name for the cardinality of this maximum independent set? Yes, there is. We will see the definition for that now. So, the definition for independence number is the number of vertices in a maximum independent set is called the independence number of G and that is denoted by alpha of G. That is, alpha of G is nothing but the maximum of the set of cardinality of A where A is an independent set in G. Now, let us see the definition of a maximal independent set in a graph. So, definition is a maximal independent set of G is an independent set that is not a proper subset of any other independent set in G. So, definition of covering: a subset K of V is called a covering of G if every edge of G is incident with at least one vertex of K. Let us see the definition of a minimum covering in a graph. A covering K is said to be a minimum covering if there is no covering K naught of G such that cardinality of K naught less than cardinality of K. So, here also does there exist a special name for the cardinality of this minimum covering? Yes, the answer is covering number. We will see the definition now. The number of vertices in a minimum covering of G is called the covering number of G and is denoted by beta of G. Now, let us see the definition of a minimal covering in a graph. So, definition is a covering K is said to be a minimal covering if there is no covering K dashed of G such that K dashed is a proper subset of K. So, now we will see the definition of edge independent set. A subset M of the edge set E of a graph G is called an edge independent set or matching if no two edges of M are adjacent in G. Next, let us see the definition of an edge covering in a graph. An edge covering of G is a subset L of E such that every vertex of G is incident to some edge of L. We note that thus an edge covering of G exists if and only if delta greater than 0. Next, let us see the definition of an edge covering number in a graph G. Definition of that is the number of edges in a minimum edge covering of G is called the edge covering number of G and that is denoted by beta dashed. Now, let us see an immediate result. We note that beta dashed of G is greater than or equal to alpha of G. Let us see an example. Here I am having a graph with 7 vertices and 10 edges. I named that graph as G. For this graph, we are going to discuss about vertex independent set, maximum and maximal independent set with respect to vertices, and vertex covering set and minimal covering and minimum covering with respect to vertices. So, vertex independent set we mean by the word it is a collection of non-adjacent vertices. So, here we are going to collect all the non-adjacent vertices. Consider this set V1, V4. So, V1 and V4 here, V1 and V4 are non-adjacent, which means that this particular set is a independent set. So, here the cardinality is 2, and if we consider V1, V5, V1 and V5 these two vertices are also non-adjacent, which means this is also an independent set. So, in vertex independent set, even if we consider a single set, that is singleton set, that is also independent, because there is no other vertex to be adjacent with, which means that here the lower bound, that is the cardinality of the lower independent set is already known to us, which means that we are not going to bother about the minimum independent, whereas our focus will be on maximal independent. So, we will be discussing about maximal independent set and maximum independent set. Okay, first let us consider this set V1, V4. So, I am going to say this set as a maximal independent set, which means according to the definition of maximal independent set, so the independent set that I am going to consider, this should not be a proper subset of another independent set. So, if we consider V1 and V4, I cannot add any other vertices to make this as an independent set. Likewise, actually if I add any vertices to this set, that set that I am going to get, that won't be another independent set, which means this set is not a proper subset of an independent set, which imply me that this is a maximal independent set. So, consider V1, V5, V3, that is V1, V5, V3. This is also an independent set, but here the cardinality is 3. So, in this set also, if we add another vertex, that set, the resulting set won't be independent, which means this is also maximal independent set. So, we mean by maximal here, we are not going to look at the cardinality here, we are just looking at the set, and the set that we are going to consider should not be a proper subset of another independent set. So, coming to the maximum independent set, so here I am going to speak about this with respect to the cardinality of that set. So, among all the independent set, the cardinality I have to consider, the cardinality should be the maximum one, that is I am going to call this as V1, V5, V3 as maximum independent set. Here the cardinality is 3, which means that here I cannot find a vertex set, that is independent vertex set with the cardinality greater than 3, which means I cannot find a vertex set, that is set of all independent vertices with cardinality as 4, that is I cannot find 4 vertices which are independent to each other. So, I am telling like this is the maximum independent set, and the cardinality is 3, the independence number I am denoting by alpha of g, that is 3. So, we discussed about vertex independent, maximal independent set and maximum independent set with respect to the vertices for this graph G. So, similarly, we are going to discuss about vertex covering and minimal vertex covering and minimum vertex covering with respect to the graph G. So, by vertex covering we mean that it is a set of all vertices that cover all the edges in that graph. So, here listen, so if I consider all the vertices here, what will happen? If I consider V1, V2, V3, V4, V5, V6 and V7, eventually that will cover all the edges. So, here there is no point in finding the maximal covering set or maximal covering number, because that is already known to us. If we have to consider all the vertices. So, here our focus will be on minimum covering and minimum covering number. Okay, so first consider this set V1, V2, V6, V7, V4. So, if I consider V1, V1 will cover the edges E1 and E10, and V2 will cover the edges E2, E9, E7, V6 will cover E6, E8 and E10 is already covered here, and V7 will cover E7, E8, E5 and V4 will cover E3, E4, E5 is already covered here. So, all the 10 edges are covered by the vertices V1, V2, V6, V7, V4. We mean that all the 10 edges are incident with at least one of the vertices that we considered. So, this is a vertex covering, this is just a vertex covering here, covering set. And when we speak about minimal vertex covering, as we did in maximal independent set, this is minimal vertex covering. So, the set that I am going to consider, that should not have a proper covering set. So, listen here V1, V2, V6, V4. So, if I remove any one of the vertices, all the edges won't be covered in this set. For example, V1 will cover E1 and E10, V2 will cover E2, E7, E9, V6 will cover E6 and E8, V4 will cover E3, E4, E5. So, what will happen if I remove the vertex V4? If I remove the vertex V4 from this set, I will be left out with V1, V2, V6 that won't cover E3 and E4, which means that there are two edges, actually that won't cover E5 also. So, E5 will be covered by V6, E3 and E4 won't be covered in this set V1, V2, V6, which means that that is true for V1, V2, V6 also. So, in this set if I remove any one of the vertices, all the 10 edges are not covered by the resulting set. That imply me that this set does not have any proper covering set. So, this set I am calling as minimal vertex covering. The same holds for this set also, V1, V7, V2, V4, V5. This is a covering set with 5 vertices. So, here if I remove any one of the vertices, not all the 10 edges will be covered here. So, this is also minimal vertex covering because there is no proper subset that covers all the vertices. So, as I already told you, here we are interested in finding the minimum vertex covering number or minimum vertex covering set. So, here we are having a covering that contains 5 vertices, we also have a covering that contains 4 vertices, and we cannot find a vertex set that contains only 3 vertices that covers all the 10 edges. You can see here we cannot find a vertex set that contains only 3 edges, 3 vertices trying to cover all the 10 edges. So, that tells me clearly my minimum vertex covering set will consist of the 4 vertices V1, V2, V6, V4, and my cardinality is 4, that is beta of g, that is minimum covering numbers noted by beta of g is 4. We have already seen the definition of edge independent set. The edge independent set is also called as matching. We will now see the definition of maximum matching. A matching M of G is maximum if G has no matching such that cardinality of M dash greater than cardinality of M. Next, let us see the definition of a maximal matching in a graph. A matching M is maximal if G has no matching M dash strictly containing M. Does there exist a special name for the number of vertices in this maximum matching? Yes, we have. That is edge independence number. The number of edges in a maximum edge independent set is called the edge independence number and is denoted by alpha dashed of G. Next, let us see the definition of an M saturated vertices in a graph. A set S of vertices of G is said to be saturated by a matching M of G or M saturated if every vertex of S is incident to some edge of M. A vertex V of G is M saturated if the set containing V is M saturated, otherwise V is M unsaturated. Let us see an example. So, this is a graph containing 7 vertices and 10 edges. So, for this graph we are going to find edge independent set or matching, maximal edge independent set and maximum independent set, and edge covering, minimal edge covering and minimum edge covering. So, consider the set E1 and E3. So, E1 is incident with V1 and V2, whereas E3 is incident with V3 and V4. These two edges E1 and E3 has no vertices in common, which means the set containing E1 and E3 is an edge independent set, or we call this set as a matching. So, what happens if I include a edge E2 to this vertex, that is E1, E2 and E3. So, if I include the edge E2 here, that will cover V2 and V3, that is here E1 is incident on V2 and E2 is incident on the same vertex V2, which means here they have vertex V2 as common. So, we cannot consider E1, E2, E3 as an independent set, which means E1, E3 is an independent set, and if we consider E7, E6, E3, E7, E6 and E3. So, as these edges do not have any vertices or vertex in common, we can say this set is itself an independent set or matching. So, here as I told, as we discussed with respect to vertex covering, here we are not interested in finding the minimal set or minimal independent set, because even if we consider a vertex containing single edge, that itself will be independent. So, here also we are going to focus only upon the maximal matching or maximal independent set. So, maximal independent set, consider this set containing E9, E3. So, according to the definition, for this set, if I am able to add an edge to this set so that the resulting edge is also independent, then we cannot say the set is maximal independent set. So, maximal independent, I should not be able to add any edge to this set. So, E9 and E3, consider E9 and E3, E9 and E3. So, E9 is incident on V2 and V6, which means that I cannot add these edges E1, E10, E6, E7, E8, and if consider this E3, so if I am considering E3, I cannot add the remaining edges E2, E4, E5 also. So, which means E9 and E3 alone is a max independent set. I cannot add any edge to this set. That tells me E9 and E3 is a maximal independent set. So, and consider E1, E3, E6, here also I cannot add any edge, so that the resulting edge is also independent. So, this set is also maximal independent. So, now let us discuss about maximum independent set. So, when I speak about maximum, here I am interested in finding the cardinality of that set. So, the cardinality here is 3, E1, E3, E6, and this is the maximum number. So, I cannot add any edge to this set so that the resulting edge is also independent. So, here the maximum number is 3, that is alpha dashed edge independence number, that is also 3. Next, we will find edge covering as well as minimum edge covering for the same graph G. So, we mean by edge covering, it is a set of all edges that cover all the vertices of the graph. So, here we have 7 vertices. We already know each edge will cover exactly 2 vertices. So, as we have 7 vertices here, we should have 4 edges to cover all the 7 vertices. So, consider this E1, E2, E5, E6, E7. Here we have 5 edges, and these 5 edges will cover all the 7 vertices. For example, E1 will cover V1 and V2, E2 will cover V2 and V3, E5 will cover V7 and V4, E6 will cover V6 and V5, E7 will cover again V2 and V7, which means all the vertices are covered by this set. So, this is also by edge covering, but here we are interested in finding minimal edge covering, because even if we include all the edges, that will eventually cover all the vertices. So, here we are not going to bother about the maximal covering set or maximal covering number, whereas we are going to focus our attention to minimal edge covering. So, if consider this E1, E7, E3 and E6. So, we mean by minimal, so minimal edge covering is nothing but we cannot able to remove edge from this set, so that the resulting set is also edge covering. So, consider E1, E7, E3, E6. If I leave E1, what will happen if I leave E1? So, I have to get an edge in this set that will cover V2 and V1. So, that which means that I should have included E10, E9 or E7, E8. So, here if I remove E1, I do not have any other edges to cover the vertex V1, which means this is a minimal covering. I cannot find a proper subset of this set that is a covering set. So, this is a minimal covering, and when we speak about minimum covering, we are interested in finding the cardinality. So, the cardinality here is 4. As I told already, it should have exactly 4 edges. So, the beta dashed of G is equal to 4. So, you can see here this is also a minimum covering set, and this is also minimal covering set. We cannot find a proper subset of this set that covers all the vertices. So, here beta dashed of G is equal to 4. And now let's discuss about the saturated M saturated set. So, we are going to denote the independent set of this graph E1 and V3. We already discussed here. So, I am going to call that set as M, capital M. M is equal to set containing E1 and E3. So, we mean by M saturated, what we are going to do here is we are going to collect the vertices which are incident upon E1 and E3. So, here if I consider V1, E1 is incident on V1. So, V1 is M saturated. Look at the vertices in the set. V1 is M saturated, and consider V2. So, V2 is incident, E1 is incident on V2. So, V2 is also M saturated. So, consider V3. So, here V3, E3 is incident on V3. So, here V1 is also M saturated, V2 is also M saturated, V3 is also M saturated, which means the set containing V1, V2, V3 is also M saturated. So, consider this set V1 and V6. So, look at this vertex V1, E1 is incident on V1, which means V1, the vertex V1 is M saturated, and consider the vertex V6. So, E1 is not incident on V6, and consider E3, E3 is also not incident on V6, which means the vertex V6 is not M saturated. That tells me the set containing V1 and V6 is also not M saturated. Let us see a theorem relating independent set and covering in a graph. Theorem 1. A subset S of V is independent if and only if V minus S is a covering of G. We shall see the proof now. Let G is equal to V comma E be any graph. A subset S of V is independent if and only if no two vertices in S are adjacent in G. That is, if and only if every edge of G must be incident to a vertex of V difference S. This is the case if and only if V difference S is a covering of G. Next, let us see a corollary for the above theorem. For any graph G, alpha plus beta is equal to n. We shall see the proof now. Let S be a maximum independent set of G. Then, by the previous theorem, V difference S is a covering of G, and therefore, cardinality of V difference S is equal to n minus alpha, that is greater than or equal to beta. Thus, alpha plus beta is less than or equal to n. Take this inequality as 1. Similarly, let C be a minimum covering of G. Then, V difference C is an independent set in G, and so cardinality of V difference C is equal to n minus beta, that is less than or equal to alpha. Thus, we have alpha plus beta is greater than or equal to n. Consider this inequality as 2. So, from 1 and 2 we can say alpha plus beta is equal to n. So, we will see a theorem related to the conic and Egger-Verry. For every bipartite graph G, alpha dashed of G is equal to beta of G. Next, we will see a theorem, that is theorem 3. For any graph G for which delta greater than 0, alpha dashed plus beta dashed is equal to n. We shall see the proof now. Let M be a maximum matching in G, then cardinality of M is equal to alpha dashed. Let U be the set of M unsaturated vertices in G. Since M is a maximum matching, U is an independent set of vertices with cardinality of U is equal to n minus 2 alpha dashed. Since delta greater than 0, choose one edge for each vertex in U incident with it. So, you will see a graph in the screen. That graph illustrates edge relationship. Let F be the set of all such edges, then M union F is an edge covering of G. Hence, cardinality of M union F is equal to cardinality of M plus cardinality of f, that is equal to alpha dash plus n minus 2 alpha dash, that is greater than or equal to beta dash. Thus, n is greater than or equal to alpha dash plus beta dash. Now, let L be a minimum edge covering of G. Then, cardinality of L is equal to beta dash. Let H is equal to G of L be the edge subgraph of G defined by L, and let MH be a maximum matching in H. Let U denote the set of MH unsaturated vertices in H. As L is an edge covering of G, H is a spanning subgraph of G. Therefore, cardinality of L minus cardinality of MH is same as cardinality of L minus MH, that is greater than or equal to U, cardinality of U, that is equal to n minus 2 cardinality of MH. Thus, we have cardinality of L plus cardinality of MH greater than or equal to n. Since MH is a matching in G, cardinality of MH is less than or equal to alpha dash. Thus, n is less than or equal to cardinality of L plus cardinality of MH, that is less than or equal to beta dash plus alpha dash. So, hence we have alpha dash plus beta dash is equal to n. Let us see a corollary due to conic. If G is a bipartite graph with no isolated vertices, then alpha of G is equal to beta dash of G. So, by theorem 1 we have alpha of G plus beta of G is equal to n. So, by the theorem that we already done, we have alpha dash of G plus beta dash of G is equal to n. Thus, we have alpha of G plus beta of G is equal to alpha dash of G plus beta dash of G. So, by theorem 2 we have alpha dash of G is equal to beta of G. Hence, alpha of G is equal to beta dash of G. Let us see some problems on independent sets and coverings. Problem 1, question is, for each alpha, alpha dash, beta and beta dash, characterize the simple graphs for which the value of the parameter is 1. For the solution, consider a simple graph G. Alpha of G is equal to 1 if and only if any two vertices are adjacent. Thus, the independence number is 1 if and only if G is a complete graph. Alpha dash of G is equal to 1 if and only if G consists of a triangle or a non-trivial star plus isolated vertices. Suppose that G consists of a triangle or a non-trivial star plus isolated vertices. By deleting the end points of any one edge in such a graph leaves no edges remaining. Thus, alpha dash of G is equal to 1. Conversely, suppose alpha dash of G is equal to 1, ignore the isolated vertices. Let V be a vertex of maximum degree. If every edge is incident to V, then G is a star. Otherwise, there exists an edge E which is not incident to V, shares an endpoint with every edge incident to V. Since E has only two endpoints, D of V is equal to 2, and there is only one such edge E. Thus, G is a triangle. Beta of G is equal to 1 if and only if one vertex is incident to all edges. Thus, the vertex covering number is 1 if and only if G is a non-trivial star plus isolated vertices. Since every edge covers two vertices, beta dash of G is equal to 1 requires that n of G is equal to 2, and indeed beta dash of K2 is equal to 1. Thus, beta dash of G is equal to 1 if and only if G is equal to K2. Several other problems and their solutions are given in the script. For better understanding, please go through all those things in that. Conclusion: in this module, we discussed about vertex independence set and vertex independence number, maximal and maximum independence set with respect to vertices, as well as we discussed about edge independence set or matching. We discussed about their maximum and maximal edge independence set, and we also discussed about vertex covering and minimum vertex covering and minimal vertex covering also. we discussed the same definitions with respect to edges, that is edge covering number, minimal edge covering and minimum edge covering. So, I hope this module will be useful to you in future. For better understanding, please try to answer some of the assignments and quizzes given in this course. Thank you.